Hello, Algebra 2. It's Mrs. Langford. I've got some more notes for you over angles and radian measures, so you need to be in your notes packet that Concept 34 notes. Make sure you've also watched the first video with the woman explaining radian measure before you take these notes. So this is where we'll be in the packet if you find this graphic, and I'm going to start just where she left off. So I'm going to show you how to convert from degree to radian measure and then from radian to degree. So right here are the conversion rates below, and I'm going to show you where those come from. So this is one of the last screens on her video, and notice that she has pi radians equals 180 degrees, which is a straight line. So we're going to start from that thought. So if we divide both sides by pi, then we have 1 radian equals 180 degrees over pi. So we're going to use that as a conversion factor to convert to degree. So when you have a radian measure for an angle and you want to convert to degree, you can use that. So we'll start with that same thought, but I'm going to write the degrees on the left-hand side and I'm going to solve for degree. So now we can see that 1 degree equals pi over 180 degrees. So we'll use that to convert a degree measure to radian. So those are our two conversion factors that we'll multiply by to convert angle measures. So now let's do some problems. So look at problem A. It says convert between degree measure to radian or radian to degree. So we start with degree, so you want to take it times the conversion factor of pi over 180 degrees. We always leave in exact form, so that means in terms of pi as a reduced fraction. So that would be 120 pi over 180. Notice our degrees divide out, so we're left with 2/3 pi, or 2 pi over 3 radian. For B, which starts in degrees, we will also convert to radian. So we'll take that times our conversion factor, and we'll get 135 pi over 180. It should be, I didn't mean to write 5 there. So it will be 3/4 pi or 3 pi over 4. With radian, because it's in terms of just a number, we do not need to label. With degrees, we always need to put the degree label. So here we're converting negative 40 degrees to radian. We'll take it times our conversion factor and then reduce that. So we get negative 2 pi over 9. Now we have radian. I can tell that not just because the pi is in my expression on D, but because there's no degree label. So I need to convert that to degree by taking that times 180 degrees over pi. Notice the pi's will divide out, and you'll get negative 180 degrees over 12. See how the degree does not divide out, and it shows up. So that is our unit. Same thing for the 5 pi over 4. We'll take it times our conversion factor. Our pi's divide out, and so we multiply and get 900 degrees divided by 4, which is 225 degrees. And finally, when we start with a decimal, then that is our signal that we can go ahead and estimate our answer, which means give our answer in decimal form. Also, that does look like a degree number, but there's no degree marking, so technically that is radian. So we're going to convert it to degrees. So on my calculator, I get negative 417 and some decimals, and so I'm just going to round to ones place. So if you start with a decimal, you can end with a decimal or with rounding, estimating. All right, let's do some more. And remember, I'm going quickly, so you can pause this video whenever you need to get these notes down. So now we're converting 200 degrees. And so I know I needed to convert it to radian, so I'll take it times my conversion factor. My degrees divide out, and I get 210 pi over 180, or 7/6 pi. Negative 45 times pi over 180 degrees. So again, I'm going to leave it in exact terms. I'll convert this one 2 degrees as well. Now this is in radian, and notice if it starts as a negative angle, it's going to end as a negative angle. So I get negative 540 degrees over 4, which will reduce to negative 135 degrees. All right, now look at this graphic. There are a couple more things that we can find. So a sector is a region of a circle that's bounded by 2 radii and an arc on the circle. So the central angle, theta of a sector, is the angle formed by those 2 radii. So here are some simple formulas to find that arc length that you see marked and the area of the circle. Sorry, sector of the circle. So for arc length, we have S, and that stands for arc length, equals R, which is the radius, times theta. And for area, it's the area equals 1/2 radius squared times theta. The only important thing, well, it's not the only important thing, but one of the important things is that the angle is measured in radian. All right, so read that problem, and my writing has already started, but let's talk through. So when a CD player reads information from the outer edge of a CD, the CD spins about 200 revolutions per minute. At that speed, through which angle does a point on the CD spin in 1 minute? So we can take those 200 revolutions per minute, and then we know that there are 360 degrees per revolution. So notice our revolution will divide out for us, and we'll be left with degree. We just take 200 times 360. So in a minute, that CD will turn through an angle of 72,000 degrees. Now in radian, so one full, if you remember from the first video, one full revolution in radian is 2 pi. It's related to the circumference of a circle. And so notice our revolutions will divide out again. And then 200 times 2 pi, that'll be 400 pi radian that CD will spin through in a minute. All right, so we have a softball field, and it forms a sector, part of a circle with the dimensions shown. So we're going to find the length of the outfield fence and the area of the field. I'm going to find lengths first and then area. So I'm going to use that arc length formula, but first I want to convert my 90-degree angle to radian. So I'll take it times my conversion factor and simplify. So I'm going to use the formula that arc length equals the radius, which is 200, times my angle in radian. So it'll be 100 pi, or about 314 feet long for that outer fence. Now 13 says, what if the fence is actually 220 feet? Very similar problem, except we'll have 220 for our radius. And so 110 pi, or about 345.5, or 0.6 feet. Now to find the area, we'll have 1/2 times that radius squared times the angle in radian. So that will give us about 10,000 pi, or 31,416 feet squared. And if we extend that fence a little more to 220 feet, then we'll have 12,000 pi, or 38,000 and approximately 13 feet. All right, let's see if I can pause this for a moment. Okay, so 28, in a man's shot put event at the 2012 Summer Olympic Games, the length of the winning shot was 21.89 meters. So a shot put must land within a sector having a central angle of 34.92 degrees to be considered fair. And I don't know if you can see or if this picture is coming up well on the video, but that is a picture of a shot put area. So the officials draw an arc across the fair landing area marking the farthest throw. So we're going to use that 21.89 meters for our radius, find the length of the arc. And we're going to use a 32 and 92/100 degree. So the first thing that we need to do is to convert that angle. So it starts with the decimal, so we're going to go ahead and estimate it. And I just went to 4 decimal places. So our arc length will be the radius. Well, I actually did the angle first in radian times our radius. And so that's approximately 13.3 meters is what the arc length is. Part B, we're going to find the area of that sector. So we'll have 1/2 times our radius, which is 21.89 squared, times, our angle. And so our area is approximately 146 meters squared. All right, so this concludes the rest of the notes on angle and radian measure. Again, I really hope you watch that video that I posted first. She gives some really good explanation and information about where the radian, what a radian is and where it comes from. So please go and watch that if you have not. Now you're ready to do all of your Concept 34 practice in Math Excel.